Today I will present our work on ResPipe, Resilient Model Distributed and Training at Edge Networks. This is a collaborative work with Professor Steph Gru and Professor Kyun Ju. The traditional approach to distributed deep neural network is data distributed learning, which partitions and distributes data to workers as illustrated in a master worker setup in this figure. In this setup, the data is partitioned and many times as there are workers in the system and all workers training multiple instances of the same model on different subsets of the training dataset. The worker applies the same algorithm to different datasets. The same model is available to all workers after update at the master device. Data distributed learning, also called data parallelism, has been frequently used as a de facto distributed learning mechanism in practical systems, especially in multi-GPU platforms. This approach, although has good convergence properties, has high communication and storage cost, which puts a strain especially on edge systems. Excessive communication among computing entities due to frequent weight synchronization in data distributed learning increase the transmission delay, which increase the overall training delay. Furthermore, computing entities should receive and store all the weights, which may not flexible for large model and computing entities with limited storage. Model distributed learning is an emerging approach where layers or parts of a training model are distributed across a worker as seen in this figure. In these setups, no single worker has a complete model, but it is distributed across all workers. Thanks to distributed model across multiple devices, the whole model does not need to be exchanged among master and workers, which permitting to reduce the communication and the storage cost. This approach has been recently investigated in multi-GPU platforms as listed in these papers. Distributed DNA training in edge systems has unique challenges as compared to multi-GPU platforms due to the heterogeneous and the dynamic nature of edge computing system and resource as well as unreliable and delayed computing entities. Furthermore, model distributed learning is more vulnerable to delayed and failing workers as compared to data distributed learning because workers depend on each other to collectively train the distributed model. In this paper, we focus on model distributed in training at edge networks, where edge device may be delayed or fail during training. We designed ResPipe, a novel resilient model distributed in training algorithm, where layers of a DNA training model instead of the data are distributed across a worker. ResPipe is resilient against delayed failing workers thanks to proactively exchange weights of the model among workers. We consider the master worker topology via the D2D connections. Workers may fail or sleep or leave the network before finishing their assigned computing tasks. Also, workers incur probabilities delay in responding to the master, where the delay has two components: transmission delay for exchange data, model, and parameters, and the computation delay. In our learning model, we have the training set A, the label vector Z, and the weight vector is the X. So the goal is to minimize the loss function via a gradient design like algorithm. Now I'll explain how the model distributed learning works via a talk example. Let us consider we train an L-layer fully connected neural network with dataset A1 to AM. There are key neurons in each layer. The goal is to learn the model X. Layers X1 to XL1 are assigned to the worker 1. XL plus L1 plus 1 to XL2 are assigned to the worker 2, and XL2 plus 1 to XL are assigned to the worker 3. So each worker processes the weight matrix of the layers that it handles. Then it forwards the activation vectors of its largest layer that is handled to a neighboring worker. For example, the worker 1 will forward the UL1 to the worker 2. Similarly, worker 2 will forward the UL2 to worker 3. This completes the forward propagation phase. In back propagation phase, workers calculate the error vectors of the layers that they handle, and they send the error vectors of the smallest layer to their neighbors. For example, worker 3 sends the VL2 plus 1 to the worker 2, and worker 2 sends the VL1 to the worker 1. Finally, each worker updates the weights that they handle This completes the backpropagation phase. Model distributed learning is promising to reduce the communication and the storage cost, as workers do not need to exchange and store the whole model. However, a pipeline is crucial in model distributed learning so that the workers should not be idle waiting for the update of the other workers. For example, the worker 1 in example 1 stay idle between the transmitting the UL1 and the receiving the VL1 plus 1, which is not efficiency. Pipeline addressing this issue by keep workers busy all the time. An example pipeline produced based on the pipe dream is demonstrated in this figure, where the Wi is the ith worker in the system, and the main idea behind the pipeline is to keep workers busy by processing a bunch of the data instead of the processing data one by one. In this figure, a mini bench size is 4, the number in the box indicates the data ID, and the black color represents the forward propagation, while the right color represents the back propagation. We assume that the forward and backwards takes one time unit, as seen after the initialized periods. The workers are kept busy. A crucial challenge of model distributed and training is the heterogeneous and time-varying resource of the edge device, including the computing power, storage, battery, bandwidth, and so on. Furthermore, struggling workers or failing potentials affect the performance of the model distributed learning. For example, if the worker 2 in example 1 is delayed, this will delay all the calculations. Thus, it is imperative to develop a resilient model distributed and training framework. As a solution, we designed the ResPipe. ResPipe provides resiliency by introducing redundant weight exchange among workers. In this example, worker 2 and worker 3 fails after some times. Those red boxes indicate the unresponsive workers. Although model distributed learning with or without pipeline fails in this scenario, the ResPipe keeps training the model thanks to redundant weight exchange. More formally, we assume that Z workers out of N could be delayed or failed during the DNA training. Each worker in ResPipe keeps track of their Z immediate neighbor workers and sends their weights to those Z workers at every T time units. In our Android test bed, the master device keeps track of their workers and informs each worker about their Z immediate neighbors. Peer discovery mechanism can be applied in large and decentralized systems. We evaluate the performance of ResPipe in a real test band consisting of Android-based smartphones. We consider a topology with 1 master and 3 and 5 workers in 2 different scenarios. The master device is a Google Nexus 5, and the workers' devices are all Google Nexus 6Ps. Since for this set of the experiments, the master node will not need to perform intensive computations, we have utilized the relatively worker Google Nexus 5 as the master node. Master and worker device are connected to each other via the Wi-Fi Direct. We demonstrate the performance of the ResPipe as compared to model distributed learning and the data distributed learning. This figure shows the accuracy of the classification of the trained model versus the time in minutes during the training for the distributed training for a CNN over MNET dataset. The input is a 28 by 28 grayscale images. I begin with the first layer. The CNN layers are given by the sequence C8, M2, C16, M2, C32, M2, F128, and F10, where the CI represents a convolution layer with I 3 by 3 by key filters applied to all the key channels of the preceding layers. M2 is a 2 by 2 max polling layer, and the FG represents a fully connected layer with the G neurons. All convolution layers, as well as the fully connected layers, are followed by a sig mode activation functions. In these setups, the second worker operates at its full performance, which is on mode for 5 minutes, and the fail for 1.5 minutes, which is off mode. Its on-off mode repeats itself. Initially, CNN layers C8 and M2 are located at worker 1, layers C16 and M2 are located at worker 2, and the layer C32, M2 and the fully connected layer 128 and the F10 are located at worker 3. The redundant wait exchange period of the ResPipe is t equal to 30 seconds. As seen, ResPipe improves over data distributed training thanks to reduce the communication cost by distributed model itself rather than the data. And ResPipe also improves over the pipe dream thanks to the provide the resiliency. Now we consider the second worker operates at its full performance, which is on mode for 5 minutes, and fail for 5 minutes, which is off mode. As seen, the improvement of ResPipe increased when the off durations of failing workers increased from 1.5 minutes to 5 minutes. This figure shows the accuracy versus time graph for a 5 worker scenario, and we have the following scene models. The second worker fails for 5 minutes at every 10 minutes. ResPipe improves both convergence time and accuracy as compared to pipe dream and data distributed learning thanks to provide the resiliency. To conclude my talks, we focused on model distributed learning with pipelining. Our goal is to provide the reliability to model distributed learning. So we developed the ResPipe, which provides reliability via redundant exchange, and in our evaluation part, we can achieve good performance.